Welcome to this explainer. If you follow the AI space at all, you've probably noticed that running a local large language model usually requires a total powerhouse of a machine. We're talking dedicated GPUs, massive amounts of high-speed RAM, and processors that basically need their own cooling fans just to keep from melting. But recently, developers have been shipping these smaller, leaner models built specifically for mobile devices and limited hardware. So that brings up a really fascinating question. Just how limited can that hardware actually be? Today, we're diving into a wild tech experiment that tries to pull off the seemingly impossible. We are going to look at running local AI entirely offline on an archaic, severely underpowered Chromebook. Here's how we'll break this down. First, we'll look at the worst-case device. Second, the actual need for offline AI. Third, finding the software solution. Fourth, setting realistic performance expectations. And finally, the value of offline note synthesis. Let's kick things off with Section 1, the worst-case device and its hardware constraints. To truly appreciate this experiment, we really have to look at our baseline device here. It's a 4 to 5-year-old Acer Chromebook. And the kicker? It has a meager 4 gigabytes of RAM. Now, if you're familiar with AI models, you know they are incredibly memory hungry. They need RAM just to load the neural network weights before they can even think about generating a single word. And making matters worse, there's no dedicated graphics card. So that tiny pool of system RAM, it has to be shared directly with the integrated graphics. And honestly, if memory wasn't a tight enough bottleneck, storage is another massive hurdle. This device is left with just 5 gigabytes of free space on its tiny 32 gigabyte SSD. Modern AI models can easily eat up tens of gigabytes, which means the options for downloading a local model are incredibly restricted right out of the gate. Finally, to round out this absolute worst-case hardware profile, we have the processor. We're looking at a passive-cooled 2-core Intel Celeron chip paired with Intel UHD 600 graphics. Let's be real, this machine was built specifically for keeping a handful of browser tabs open, typing some documents on the go, and holding a charge for a long flight. It was absolutely not, by any stretch of the imagination, built to process artificial intelligence. Moving on to Section 2, the offline AI need, and what happens when networks fail. Now, you might be wondering, why even bother? Under normal conditions, this little Chromebook handles cloud-based chatbots completely fine in the web browser. Whether you're hitting up Claude, ChatGPT, or Gemini, there's really no noticeable lag. So why go through the pain of running local AI? Well, because when the power goes out long enough to drop the cell towers, your mobile data connection completely vanishes. And when the internet goes down, all those powerful cloud-based tools just cease to exist. The core motivation here is true digital independence. It's about having a reliable synthesis tool that stays fully functional, even when both the power grid and cellular networks fail. That brings us to Section 3, finding the software solution and bypassing the terminal. Usually, the traditional, flexible route for running local AI involves diving into the command line to compile a program like a llama or llama.cpp. But trying to compile code on a passive-cooled Celeron processor with only 2 cores and basically no storage, that is a total recipe for disaster. But here is the really clever workaround. Modern Chrome OS actually runs 2 completely separate Linux-based layers beneath the surface. One is for proper Linux desktop apps, and the other is dedicated entirely to running Android apps. By simply turning on the Linux developer environment, the author was able to completely bypass that complex command line compiling. Instead, they just used the Google Play Store to download a mobile Android app capable of running local AI. Pretty smart, right? Of course, it definitely wasn't smooth sailing on the very first try. The initial attempt used an app called LLM Hub, paired with the Ministral 3 model. And predictably, the second the chat tried to load, the app instantly crashed. The model just demanded way more RAM than the Chromebook could ever provide, but then came the pivot. They found this tiny open-source app called LM Playground. It comes in at under 13 megabytes, and it ran the Gemma 4 E2B model, which is a model specifically optimized for mobile devices. Now, the app did throw this desperate warning saying the model needed over 3 gigs of RAM and might be unstable. But remarkably, it loaded. It didn't crash at all. The whole crazy setup actually worked. Now let's get into Section 4, realistic performance expectations. It's slow, but functional. Okay, so it's one thing to get an AI to load without instantly crashing the computer. It is an entirely different thing to actually use it. And here's the hard truth. The model processes text at a painfully slow 0.3 tokens per second. And to understand why it's dragging so much, you just have to look at the architecture. Remember, this is an x86 Intel chip trying to run an ARM-optimized Android app inside a Linux container running on Chrome OS. It's buried so many translation layers deep with almost zero raw processing horsepower to push it along. To put that into perspective, at zero point 0.3 tokens per second, you are waiting a seriously long time just to watch a single sentence slowly, painfully form on your screen. And as for its actual intelligence once it finishes typing, well, it got the classic AI strawberry spelling test completely wrong, claiming the word only has 2 R's. Though to be totally fair to our little Chromebook, much larger cloud models still trip up on that exact same test all the time. Ultimately, the AI does function, but using it requires immense, almost Zen-like patience. Because the speed was so agonizingly slow, the author had to apply some really aggressive optimizations. They issued strict system prompts to keep the responses short, skipped chain of thought processing entirely, and turned thinking mode off completely just to claw back some speed. But surprisingly, while you couldn't upload files and it lacked advanced parameter controls, this tiny little LM Playground app came packed with built-in tools. It actually has web search, web fetch, and even a sandbox JavaScript tool built right in, which requires literally no extra server setup. It even successfully pulled real-time weather data during testing, even if it did take a very long time to generate that final answer. Finally, we arrive at Section 5, Offline Note Synthesis Value and its Real-World Utility. So think about what we've got here. We have a system that is incredibly slow, lacks advanced controls, and can't handle file uploads. Sounds kind of terrible, right? But here is the massive practical success story. Despite every single limitation thrown its way, this Gemma 4 model absolutely excels at exactly what the author needed it for, which is brainstorming, light research, and organizing structured notes. If you toss it a super messy, disorganized question, it gives you back a response with a perfectly sensible, organized structure without you even having to prompt it to do so. It turns out to be a highly capable synthesis tool for making sense of complex information, completely offline. Which brings us to the end of our explainer and leaves us with one final thought to chew on. In an era where we rely so heavily on the cloud for absolutely everything, true digital independence is becoming incredibly rare. But this experiment proves that even the most underpowered, discarded hardware can actually become a self-contained hub of knowledge and organization. So I'll leave you with this question. What would you use a slow, offline, but completely reliable AI for when the grid finally goes down? Thanks so much for learning with us today, and we'll see you in the next explainer.